Hi, I'm going to be reviewing problem 1-1 in the AP Physics review book. This problem is a kinematics problem. It involves some equations, some graphs, and some particles moving along them. So you start with a particle moving along a parabolic path along the equation y equals 1/2 x squared. In part A, you're going to consider the x component of the velocity being constant, proportional to the value c. So the first question is asking you to draw the directions of the velocity vector and the acceleration vector. So, since the velocity is constant in the x direction, the acceleration is only in the y direction, and so since it's moving upwards, the acceleration will also be upwards. So it would be a vertical line coming right here. This is A. And the velocity, it's moving along this path, see? So the velocity will just be in the same direction as the movement, which would be on tangential line right here. For part 2, you're going to determine the y component of the particle's velocity as a function of x. Right now you have the, let's see, you know the component of velocity would be y. Vy is equal to dy over dt. You have dy over dx. You could calculate that from the initial equation here. But that's not in the formula here, so you have to use the chain rule to extend this out into dy over dx times dx over dt. As you can see, the dx's cancel each other out. So, from the initial formula, y equals 1/2 x squared, dy over dx would just be equal to x. So, in order to get dx over dt, you go back to the initial problem and you see that x equals ct. So, x equals ct, dx over dt would just be c. So when you multiply those together, you get Vy is equal to ct. There you go. That is part 2. For part 3, you need to determine the y component of the particle's acceleration. So the acceleration is the derivative of the velocity, so acceleration in the y direction is equal to dvy over dt, which is equal to the derivative of ct right here. So c is a constant, so you can just bring it out into the front. It's equal to c times the derivative of dx over dt. And then from here, dx over dt, you already calculated it right here, it's just c. So this now equals c squared. So now we will move on to part B. For part B, you're going to assume now that the particle follows a different velocity, and it's given by c over the square root of 1 plus x squared. And we need to show that the particle's speed is constant in this case. So first, you need to determine what the particle's speed actually is, just to determine an expression for it. To do that, we use the Pythagorean theorem. The velocity is equal to the square root of the velocity in the x direction squared plus the velocity in the y direction squared. It's just a simple matter of imagining the triangular shape of the vectors. From here, you know you have information about the x. formula here, you have it's given in terms of x. So you need to solve for x. Not x exactly, but just in terms of velocity in the x direction. So you'll take so you have your Vy. That is equal to dy over dt, as we said before. Chain rule this out, plus dx for dt, so that you can isolate the x here. Dx over dt multiplied by, sorry, I messed this up completely, equal to dy over dx times dx over dt. There we go. And from here, you know that dy over dx is equal to x from the previous part, right here. And also dx for dt is equal to the velocity in the x direction. So now you know that velocity in the y direction is equal to x times velocity in the x direction. So from there you plug it into the original formula. Velocity is equal to square root of vx squared plus x times velocity in the x direction squared. Simplify this out. And you end up with velocity is equal to velocity in the x direction squared times the quantity 1 plus x squared and the square root of all of that. Next, you will substitute in the original equation here. You have Vx is equal to c over 1 plus x squared. That goes into your v of x right here. Simplify this some more. Cancel out the square root sign. And now you can see easily here that the 1 plus x squares cancel out, and you're left with the square root of c squared, which is just c. So you can see that the velocity is in fact constant. Now, for part 2 of part B, come back to the original problem. You need to indicate the direction of the particle's velocity vector v and the acceleration at point S, and label each vector. So now the velocity vector, it's just going to be along the same path, along the path of motion. So it's just tangential here again. That's velocity, same direction as it's moving. Now acceleration, since the velocity is constant along this entire time, there is no real, all the acceleration is doing is it's changing the direction of motion. And when the acceleration is changing the direction of motion along a curved path, it's pointing towards the center. It's a centripetal acceleration, so it'll point towards the center of the arc right here. And that is the last step of the problem. I'll just show you the entire work for part B again, because it's pretty long and might have been out of focus a little bit. And that is all.